This is the nature of science video. So this we talked about the English system, right? So the English system, it was an honest attempt at a standardized measurement of measurement system, right? So without fast communication, it was very hard to standardize measurements. So common objects were used, like barley corn. So this all started in Europe, where barley corns were grown regularly, and you stack three of them together, that would be an inch. And a yard was the distance between the nose and the tip of the fingers. Now, notice how 12 barley corn inches don't quite add up to what we know as a foot. Now, a drawback to this system is that, well, barley corn aren't going to be the same length, and everybody has a different, distance from the tip of their nose to the tip of their fingers. But on a local level, this would work, right? If you were trying to build a house with, your friends or your family, you could do this because you would just pick one person and say, all right, this is the yard that we are going to use. This is the inch that we are going to use. You could build a house. But it started to break down once you started going to different towns. If you were going to sell crop to a different town, then what would happen is, well, it would start to, like, how would you know that their weight measurement is the same as your weight measurement and you're getting a fair price for what you're selling? So this was the lab that we did, the metric versus English lab. Now, what you're doing is you're going to measure the diameter of three different cans by placing the ruler on top of the cans, and then you're going to measure the circumference by placing the mark on the 0 point and roll it across the ruler, and that would get the circumference. Now, on the metric side, it's very easy to read because each one of those little dash marks is 1 millimeter, 1/10 of a centimeter. So that arrow right there, that would be 3.6 centimeters. Now, the inches side is a little bit different. On the English side, the resolution, each one of those dash marks is 1/8 of an inch. So it would have to be converted into decimal. So, if, like that arrow right there, that's 2 3/8. That's 2.375 inches. Now, once that data is collected, it was graphed, right? So that brings us to that original question: is the metric or English system more valid? So this was the data that was collected. Now, notice that the slope on each of these appear to be the same: 3.15, 3.13, and notice they're about the same, and the slopes. So both measurements of system are just as accurate. Both of them are just as precise. Both of them are just as valid because they were just made up by humans, right? You can make up your own measurement system and it would be just as valid. Now, the reason why that number is around there is because, well, the circumference divided by diameter is always going to be pi. That's going to be the ratio. So if someone were to make up their own measurement system, it doesn't matter what it is. It's just how we describe it, right? Think of the black box experiment. We weren't like humans weren't given a measurement system and says this is the universal measuring system. No, like every measuring system, the English and the metric, just as valid, just as accurate, because that doesn't change what's being measured. It just changes how it's being described. So yeah, that's what this lab was about, is to show that they're both just as accurate, they're both just as precise, and they're both just as valid. Right now, the second in the metric system is uses cesium atoms. So that valence electron of cesium, well, it oscillates states very reliably. Right, so every like over 9 billion times, that's what's defined as the second, right? So the benefits of this is that it's universal, right? Cesium atoms all over the universe will oscillate in the same way. It's based on something universal. Same thing with the meter. The meter has gone through some changes. It used to be 1/10 millionth of the distance between the equator and the North Pole. Then it was based on something physical, and now it's defined to be how fast light travels in a vacuum in a certain amount of time, and that time is measured by that cesium atom. So it's based on something universal. So the kilogram was the last thing to switch over. It used to be just an object that was in a vault in France, and this is the kilogram. But it changed. Every once in a while, it would seem to get lighter by a few atoms. And, well, once that happens, every kilogram in the entire universe has to change because that's what we define the kilogram as. But in May 20th, 2019, it switched over to something universal. So the metric system, well, is mostly used for two reasons. Number one, well, it's universal. Everything that can be measured, it's defined as constants of the universe, and it's base 10, so it's very easy to use. It's very easy to convert within the metric system, right? So there isn't a black box that was just open and it was given to us as, hey, the metric system is this, but we now use universal constants to define how we describe like things around us. So converting within the metric system is very easy. You just move the decimal point, right? So, and this diagram really does a good job of illustrating that, where that base unit, well, that would be like meters, grams, seconds, newtons, and liters. And you just move whichever way you're going, right? If you're getting smaller, you move the decimal to the right. If you're getting bigger, you move the decimal to the left. So very easy to convert. So this is some practice. So a metal rod has a length of 0.25 meters. So significant figures is going to have two significant figures based on those rules. Now, when once you convert it to millimeters, you get 250 millimeters. Now, once again, this has two significant figures. Notice no significant figures were lost. That zero is just a placeholder, because if you look at that top measurement, that whatever was used to measure that metal rod did not have the resolution to accurately measure one decimal point after. That zero is not a significant figure. Now let's look at something measured in mass. So 35.0 grams. Now that has three significant figures. That zero is accurate. Whatever was used to measure it had the resolution to measure that. Now, if it's converted to kilograms, notice it's 0.0350. That zero doesn't go away. That zero is accurate. It still has three significant figures based on the rules of significant figures. So the question is, does converting units in the metric system affect the resolution and or significant figures of that measurement? No, it doesn't. It's just a different way to describe that measurement. It doesn't get any more or less accurate when you convert. So the biggest example that can be had is if somebody's looking at somebody and say, well, that person weighs about 180 pounds. Well, the instrument being used to measure it is a person, and it has two significant figures. That's how accurate that instrument is. That zero is just a placeholder. Now, if that person were to step on that scale, well, it might be 180.0 pounds. So notice that now it has four significant figures, right? That's what affects significant figures. Whether the resolution of the instrument and whether it has an uncertainty digit or not. So that's what affects it. All right. So the Measure Up Lab was designed to go into that, and it was designed to measure different lengths of or different measurements, whether you're measuring the meter stick or length, mass, force, or time. Right. So the first part was to look at the meter stick and say what the resolution is and if it has an uncertainty digit or not, and why or why not. Same thing with the triple beam balance. Same thing with the spring scale and the stopwatch. So this is the data that was collected from that lab. Now notice that when the measurements were taken and converted, notice that no significant figures were gained or lost. If you have four significant figures with whatever you measure, if it's converted into another unit, it still has to have four significant figures. So the random errors, well, that's just the inability to take the same measurement twice. Systematic errors are defects in the measuring instrument or parallax effect. And that last question, did converting units in the metric system affect the resolution or significant figures? The answer is no, because what affects that is the resolution of the instrument or the uncertainty digit, and the uncertainty digit. So another question is, how do you record a measurement in regard to resolution and the uncertainty digit? And that was the Ruler of the World lab. So in this lab, there were 10 different lines on a piece of paper that had to be measured with a ruler. The first part was to look at the measuring stick, that transparent measuring stick, and find the resolution and if it has an uncertainty digit and why or why not. And once again, the uncertainty digit can only happen with analog instruments. So yes, this would have it. And the resolution would be 1/10 of a centimeter or 1 millimeter. So these were the this was the data that was collected, right? So notice that when they're recorded, the resolution has to be recorded and the uncertainty digit. So even though one of the lines, that first line, was 23 centimeters exactly, we'll notice that the resolution, the 1/10, recorded, and that uncertainty digit, which was a 0 because it fell exactly on that line. So that has 4 significant figures. And notice that when it gets converted, every single one of those conversions has 4 significant figures. Now, one of the conclusion questions is asking about putting that transparent measuring stick on top of uh, the another measuring stick, and notice that those millimeters don't quite match up. Well, in the beginning, yeah, they're about the same, but then as you get to about 20 centimeters, they start being off by a little bit, and then around 30 centimeters, it's almost off by a whole millimeter. Now, it says what could be done to figure out which measuring stick is more accurate? Well, the next question is what is used to define the meter? And it might have to be looked up. Well, remember, everything in the metric system is based on something universal. So if we look at that measuring system, remember, right now, a meter is defined to be how far light travels in a vacuum in that long, where the second is defined as with the cesium atom. So there is a way to figure out which one of those measuring sticks is more accurate. So one of the questions was, when using the metric system, did converting the units change the number of significant figures? The answer is no, because significant figures depends on the number of or the resolution and the uncertainty digit. And systematic errors, well, the systematic error would be that the millimeter might not be accurate. Right? That could be one of the systematic errors. All right. So, just as a final thought, remember there's too much unknown in the universe to take a break from learning. Get out there and question everything.